Welcome to Advanced Linear Algebra. Today we are going to explore one of the most beautiful and powerful results in mathematics, the spectral theorem. Imagine looking at a distorted, messy shadow of a three-dimensional object. From most angles, it is incredibly hard to measure. But if you find the absolute perfect viewing angle, everything aligns perfectly. The spectral theorem is exactly like finding that perfect viewing angle for certain matrices, allowing us to untangle complicated transformations into the simplest possible straight lines. Now that we know our goal is to untangle complex transformations, let us look at the specific type of matrix that allows this. We start with a symmetric matrix. Why does this matter? Because symmetry in mathematics always implies a deep underlying balance. A symmetric matrix is a square grid of numbers that looks exactly the same if you flip it across its main diagonal. In mathematical terms, its transpose is equal to itself. Because of this perfect balance, symmetric matrices do not distort space unpredictably. They behave like a perfect mirror reflection, setting the stage for the spectral theorem. Building on our symmetric matrix, we need to understand the tools that will form our perfect viewing angle. These are eigenvectors and eigenvalues. Eigenvectors are special arrows in space that do not change their direction when the matrix transforms them. They only stretch or shrink. The amount they stretch is the eigenvalue. The spectral theorem makes a massive guarantee. If a matrix with real numbers is symmetric, you can always find a complete set of perfectly perpendicular axes, each with a length of exactly 1, made entirely of its eigenvectors. This is called an orthonormal basis. Before we move on to the main formula, let us prove the most beautiful and important part of this theorem: why these eigenvectors are always perfectly perpendicular to each other. We start our mathematical reasoning by assuming we have a symmetric matrix A, which means it is equal to its transpose. We also assume we have two completely different eigenvectors, which we will call V1 and V2. Because they are different, they correspond to distinct stretch factors or eigenvalues, lambda 1 and lambda 2. We write down the fundamental definition of an eigenvector for both. Matrix A acting on V1 simply scales its length by lambda 1 without rotating it, and similarly for V2. Our ultimate goal for this chunk of the proof is to set up the equations so we can eventually show their dot product is exactly 0. Now we want to connect these two equations to see how the vectors relate to each other. We do this by taking the dot product of V1 with the transformed vector AV2. In matrix notation, this dot product is written as V1 transpose times AV2. Since AV2 is just lambda 2 times V2, we can pull the regular number lambda 2 out to the front of the expression. Next, we look at the exact same starting expression, but group it differently using standard matrix algebra rules. Because our matrix is symmetric, A transpose is exactly the same as A. This symmetry magic allows us to substitute our first eigenvector equation into the expression, pulling lambda 1 to the front. This connects our steps perfectly for the next phase. We have just calculated the exact same quantity in two completely different ways. So these two results must be perfectly equal to each other. We set them equal and move everything to one side of the equation by subtracting the right side from the left. This algebraic manipulation lets us factor out the common term, which is the dot product of our two vectors. This final equation tells us that the product of two numbers is 0. But we stated at the very beginning that our eigenvalues are distinct, so their difference cannot possibly be 0. Therefore, the dot product absolutely must be 0. We have mathematically proven that the eigenvectors are perfectly perpendicular, concluding the most crucial part of the theorem. So, we have proven that the dot product is 0. This brings us to a visual confirmation of what we just proved mathematically. Look at this diagram. When a symmetric matrix stretches space, represented by the red ellipse, it does so along perfectly perpendicular axes. These thick black arrows are the eigenvectors, u1 and u2. Notice the right angle square between them? They form a natural, unrotated grid for the transformation. No matter how much the space is stretched, these specific directions remain perfectly orthogonal to each other. Now that we understand what the eigenvectors of a symmetric matrix look like, let us look at how we can use them. The spectral theorem allows us to write our original matrix as a sum of much simpler pieces. This process is called spectral decomposition. Instead of looking at the matrix as one big, complicated block of numbers that mixes everything up, we break it down into a combination of simple, one-dimensional projections. By doing this, we turn a difficult multi-dimensional problem into a series of incredibly easy, independent steps. This concept leads us directly to the spectral decomposition formula. Conceptually, this formula builds the full matrix out of its fundamental perpendicular directions. Let us break down the symbols. Capital A is our original symmetric matrix. The Greek letter lambda represents the eigenvalues, which act as weights or stretch factors. The vector u represents the normalized eigenvectors, meaning they have a length of exactly 1. Finally, the term u times u transpose creates a projection matrix. As an eigenvalue increases, the influence of that specific perpendicular direction on the overall transformation becomes much stronger. Before we can build the decomposition, let us see this with a concrete example of finding the orthonormal basis. We are given a 2 by 2 matrix and we can clearly see it is symmetric because the off-diagonal numbers are both exactly 1. Our first step is to find the eigenvalues. We do this by setting up the characteristic equation, which means subtracting a variable lambda from the main diagonal and setting the determinant to 0. We calculate the determinant by multiplying the diagonal entries and subtracting the product of the off-diagonal entries. Continuing with our characteristic equation, we expand the terms in the parentheses to get lambda squared minus 6 lambda plus 9, and then subtract the 1. This simplifies nicely into a standard quadratic equation. Lambda squared minus 6 lambda plus 8 equals 0. We need two numbers that multiply to 8 and add to negative 6, which are negative 4 and negative 2. Factoring this gives us our two eigenvalues. Lambda 1 equals 4 and lambda 2 equals 2. These are the fundamental stretch factors of our matrix transformation. Now we must find the eigenvector for our first eigenvalue, 4. We subtract 4 from the diagonal of our original matrix and multiply by an unknown vector xy to get 0. This translates to the simple equation negative x plus y equals 0, meaning x equals y. We choose the simplest whole numbers, 1 and 1, for our vector. But the spectral theorem requires an orthonormal basis, meaning a length of exactly 1. We find the length using the Pythagoras theorem, which is the square root of 2, and divide our vector by it to normalize it. We repeat the exact same process for the second eigenvalue, 2. Subtracting 2 from the diagonal gives a matrix of all 1s. This translates to x plus y equals 0 or x equals negative y. Choosing the simplest values gives us negative 1 and 1. We normalize this vector by dividing by its length, which is again the square root of 2. This gives us our final answer for the orthonormal basis. Notice that if you take the dot product of u1 and u2, you get 0, perfectly confirming the orthogonality we proved earlier. Now that we have the eigenvalues and the orthonormal basis, let us use them to build the spectral decomposition of the matrix. We will construct the matrix by adding together its individual projection pieces. We start by creating the first projection matrix, P1. We do this by multiplying the first normalized eigenvector by its own transpose. The 1 over root 2 fractions multiply together to give 1/2. Multiplying the column vector by the row vector creates a 2 by 2 matrix. This matrix acts as a filter that only lets the U1 direction pass through. We do the exact same calculation for the second projection matrix, P2, using the second normalized eigenvector. Again, the fractions multiply to 1/2. We multiply the column vector by the row vector to generate the second 2 by 2 projection matrix. This matrix captures the pure direction of the second eigenvector. We now have our two fundamental building blocks. According to the spectral theorem, if we scale each of these projection matrices by their corresponding eigenvalues and add them together, we should perfectly reconstruct our original matrix. Let us set up that final addition to prove it works. We substitute our eigenvalues 4 and 2 and our projection matrices into the formula. We distribute the numbers into the matrices. 4 times half is 2 and 2 times half is 1. Finally, by adding the corresponding entries of these two matrices together, we get exactly our original matrix A. This physically proves that the complex transformation is nothing more than a combination of two perpendicular projections, scaled by their eigenvalues. We have successfully broken down the matrix. We have covered the full topic, so let us reinforce the most important ideas. First, no matter how large or complicated a symmetric matrix is, it can always be completely understood. Second, it is guaranteed to have perfectly perpendicular eigenvectors that form a clean coordinate system. Third, the spectral decomposition formula allows us to break down multidimensional problems into simple, independent, one-dimensional pieces. This is not just abstract math, it is the absolute foundation of quantum mechanics, principal component analysis, and mechanical engineering. You now have the ultimate tool for simplifying linear transformations.